So in our next section, we're going to start to talk about the specifics of MPLS in terms of what are the features, what are the functionality, why would we want to use this versus other types of tunneling techniques. We'll also spend some time talking about what are the different MPLS device roles, what are the specific operations that they perform in terms of push, pop, and swap, and then also what are the different label distribution protocols that we're going to be focusing on, not only for IGB distribution with LDP, but also with RSVP for MPLS traffic engineering, and then also BGP labeling, both for VPN-v6 and VPN-v4, and then as well as IPv4 unicast labeling when we're dealing with our inter-AS MPLS Layer 3 or Layer 2 VPN type designs. So first and foremost, what is MPLS? Specifically, the term multi-protocol label switching was originally called tag switching. Now it's an open standard, which is defined in RFC 3031. So you'll see throughout the rest of the details as we start to go into more depth of the technologies. I'll link some of the relevant RFCs here. If you want to get specific information about what is the label format or what is the LDP format, what is the RSVP format, then I would definitely recommend to take a look at those particular RFCs. There are some ones that we'll look at specifically that I'll share out on the screen and go through a couple sections that relate to specifically VPN-v4 and as well as some of the provider edge to customer edge routing protocol interaction. But the first core one then is going to be 3031, which just talks about the overall switching architecture. Now, the name itself, when we call it multi-protocol label switching, it implies that there's two different important portions to the overall feature. First is multi-protocol, which means that it is agnostic as to what type of protocol that is going inside of it, and likewise what protocol it is going over. So we'll see that there's multiple types of encapsulations that can go in the payload of MPLS, whether this is IPv4, IPv6, Ethernet, other layer 2 protocols, and then for layer 2 encapsulation that is MPLS is writing over, it's independent of whether we're running over Ethernet, point-to-point, HDLC, PPP, legacy frame relay, legacy ATM, etc. So it is, you can think of this kind of like how a GRE tunnel is a generic encapsulation, as is MPLS. Now the other one, label switching, we'll see this is how we actually make our forwarding decision, that the devices in the MPLS core are not going to be looking at the payload of the tunnel traffic. So they don't need to know the final IPv4 destination, the final Ethernet MAC address. They're going to be making their decision just on the label value. Now, as I mentioned, the first keyword, multi-protocol, means that it can have different payloads as well as going over multiple transports. Now, in our focus, we're mainly going to look at three of these, which is Ethernet over MPLS in Layer 2 VPNs, both in point-to-point pseudo-wires for virtual private wire services, and then in multi-point Layer 2 VPNs in virtual private LAN services, and then EVPN-based provider backbone bridging. But beyond that, most of our focus is really going to be on Layer 3 payloads in terms of either IPv4 for MPLS Layer 3 VPN or IPv6 in terms of 6VPE or 6PE. Now, beyond this, MPLS is extensible for future payloads. So if there's some sort of new Layer 2 protocol that eventually replaces Ethernet or an additional Layer 3 payload, IP version 7 or whatever beyond, MPLS is extensible because it is independent of what it is transporting and what it is being transported over. Now, the second of these terms, label switching, means that the devices in the middle, the MPLS switches or the MPLS routers, are making a locally significant decision based on the MPLS label number. Now, we'll see that the way that the label number is allocated is going to be arbitrary from the data plane point of view. So what I mean by this is that when the switch or the router actually goes to make its decision on a packet came in, I look at the label number, I make a decision, and then forward it outbound. The router doesn't care whether the label came from label distribution protocol, whether it came from BGP, whether it came from RSVP for MPLS traffic engineering. And we'll see there's a clear separation between the MPLS control plane and the MPLS data plane. So regardless of how we are allocating or assigning the label, the data plane forwarding decision is going to be based on this locally significant number that is only significant between you and your directly connected MPLS peer. Now, the basic logic of this is similar to how legacy frame relay switching worked or legacy ATM switching worked, where in frame relay we had an input and output data link connection identifier, or a DELC, and ATM we had an input and output virtual path identifier and virtual channel identifier, or the VPI VCI. So the point being is that this address does not have global scope like an IPv4 address would or an IPv6 address does. It's only local scope significant, locally significant, similar to a MAC address that is between the directly adjacent layer 2 devices on that particular local segment. Now, the reasons why we use MPLS mainly is going to be for transparent tunneling over the service provider network. So we saw in our previous functional example that when we're running BGP in the service provider, the devices in the core don't need to know all of the destinations, all of the sources, and this is what we sometimes refer to as our BGP-free core. The idea is that the very high-speed core routers in the service provider networks, they don't need to know the overall IPv4 Internet Global Table, they don't need to know the IPv6 table, they don't need to know about all the MPLS customers. They're going to save a bunch of routing table space and then only have to make their decision based on a few number of labels, MPLS labels, that are going to be based on the ingress edge and the egress edge of the specific provider edge devices. Now, beyond this, the other main motivation is going to be for layer 2 VPN and layer 3 VPN services. So regardless of what the transport is that the provider is using, we might have a mix of legacy T1, frame relay, ATM, etc., as well as newer Ethernet, 40 gig, 100 gig, and beyond. And like I mentioned, MPLS is multi-protocol, so it is independent of what the underlying transport is or what it is transporting inside of the payload. So from a service provider point of view, this means that they can keep their legacy equipment and then integrate all of those customers together in the same type of either layer 2 VPN or layer 3 VPN. So we'll see that this is going to be really the main focus of this class overall, and we're going to go over this in much more detail. What are the different variations for L2 VPN and L3 VPN? And we'll see that this is where the vast majority of complexity is really going to come into the overall MPLS design. Now, another important portion that we will spend time on, but it's definitely not going to be as complex as either L3 VPN or L2 VPN, is MPLS traffic engineering. Now, what traffic engineering is going to allow us to do is to utilize typically underutilized links. Like if we have 10 gig Ethernet and 40 gig Ethernet, and if we look at this from a normal IGP routing point of view, we would typically choose only the 40 gig links because we're making our decision based on the lowest cost in the network. But with MPLS traffic engineering, we can manually define policies that say, well, I want some traffic to be distributed on the older links or the slower links, or based on the type of service, maybe we have voice traffic, video traffic, that we want to make sure that that is not going over low delay circuits, like maybe satellite links. We could do this based on a user-defined policy that we are ultimately going to control. So we can give bandwidth guarantees to the application. We can do routing based on the service type. And then also one of the very important ones is going to be MPLS TE Fast Rerouter, FRR, which is going to allow us to pre-calculate backup paths in the network, which is very similar to the OSPF loop-free alternate or the BGP prefix independent convergence features. So the idea is that we're going to say, this is my primary path, this is my backup path, and then if the primary path fails, we can automatically switch over to the backup path and have a very small hit in the data plane in terms of like a 50 millisecond failover time. Now, in terms of the actual MPLS label, as I mentioned, the allocation type, or how we're actually assigning the label, is going to be independent of how it is actually switched in the data plane. So whether we're talking about label distribution protocol, BGP labeling, or traffic engineering, we're always going to be using the same type of label format, which is a 4-byte header that is used to switch the packets between the local interfaces. Now, in the 4-byte header, the main important field is going to be the actual label itself. This is how we're making our forwarding decision. Now, beyond this, we have the experimental bits, which is going to be the class of service or the quality of service that we define. We have the S bit, which is going to define which is the last label in the stack, or what's sometimes referred to as the bottom of the stack. And we'll talk about in more detail today. Why is that significant? Why does the device need to know that this is the last label? And then for a data plane loop prevention mechanism, we also have a time to live. So similar to as we do in an IPv4 packet or IPv6 packet, this is going to say if there's a control plane problem and I'm routing the packet to you and you're routing the packet back to me, eventually in the data plane, the time to live would expire, and then we would not infinitely loop the packet through the service provider core. Now, the way that the labels specifically function is that we are going to be associating them to an IP version 4 prefix, or what we call a forwarding equivalency class. So 9 times out of 10, the FEC for MPLS is the association between an IP route and a specific label number. Now, we'll see that there are other cases, like in MPLS traffic engineering or in layer 2 VPN pseudo-wire labels, that the label number can be bound to other attributes, but vast majority of cases when we're dealing with L3 VPN, this is going to be relating to an IPv4 routing binding to the MPLS label number. Now, when a packet comes in, and where the router would normally make a decision based on the IPv4 destination or the IPv6 destination, we're then going to use the label forwarding information base, or what's called the LFIB, in order to make our forwarding decision, as opposed to using the regular IP routing table or the IPv6 routing table. So the ultimate logic here is that we're going to say when traffic comes in on interface 1 and we match it and see that it has label X, we're going to change that label to a different number. We're changing it to label Y in this case, and then forwarding it out interface 2. So this means from the lookup procedure point of view, MPLS is a simpler forwarding decision than if we're looking at IPv4 information or IPv6 information, because we have these one-to-one bindings already built between the ingress interface and the egress interface. And we'll see from a verification point of view, this is one of the very important things to understand, is how do we find which particular label switch path or which LSP an individual traffic flow is going to be following, and then how do we verify this in the label forwarding information base that we're actually correctly forwarding the traffic on a hop-by-hop basis. Now, specifically in order to do this, we'll see that there are 3 different types of device roles in the MPLS network, which are the provider edge router, or PE, the customer edge router, or CE, and the provider router, or the P router. Now, the first of which, the customer edge device, or the CE, is going to be the last hop device out of the customer's network. So this is where we have our customer edge to provider edge connection, where we're going to be running typically some sort of routing protocol, whether this is an IGP or whether this is BGP, when we're referring to layer 3 VPNs, or in the case of layer 2 VPNs, we're going to be running just transparent bridging, typically running Ethernet. So the customer edge device could be layer 2 only, or it could be layer 3 aware, but in most cases, it is not going to be MPLS aware. So this means that we're going to be running just normal IP routing, like we could use a default route out to the provider, or we're going to be doing normal switching, like we're doing an Ethernet-based VPN, and then we're forwarding the traffic from the customer edge based on the MAC address table. Now, on the other side of the provider edge device is going to be the provider edge. So the provider edge, sometimes you'll see this referred to in older documentation as the label edge router, or the LER. When we're looking at either the label edge or the label switch router, those are the old terminology for the provider edge or for the provider router, for the PE and the P router respectively. Now, we'll see the provider edge router is going to be really the most important device within our scope. That this is the last hop device in the provider network that is connecting to the customer, and it's going to be the demarcation point between the customer's network and the service provider core. So this means that the PE router is going to be performing both IP version 4 or IP version 6 routing, as well as MPLS label switching. In the case of layer 2 VPNs, it's going to be doing a layer 2 decision, like a MAC address forwarding decision, or point-to-point HDLC PPP decisions, and then taking those type of layer 2 payloads and then putting that inside of an MPLS packet. So in terms of configuration, in terms of verification, troubleshooting, we'll see that the vast majority of our work is going to be done on the provider edge. Now, for the provider edge, there's going to be 2 different traffic flows that we need to look at for either traffic coming in from the customer and then forwarding it towards the core of MPLS, or vice versa, the traffic coming from the core and then forwarding towards the customer. Now, for traffic inbound that is received from the customer and going towards the core, we're going to be receiving unlabeled packets, whether these are native IPv4, native IPv6, or some sort of layer 2 payload like Ethernet. We're going to do an ingress routing lookup or an ingress switching lookup if we're doing layer 2 VPN, and we're going to be adding one or more MPLS labels and then forwarding this packet towards the core. And specifically what this operation is called is the MPLS imposition, or what's sometimes referred to as the push operation, where we're essentially having the customer edge sending us the IP packet in, the provider edge receives this, it's going to add an MPLS label, and then send this out towards the service provider core. Now, in the reverse direction, as we go from the core to the customer, we're going to be receiving packets that are already MPLS labeled. We're going to be removing one or more of these labels, doing an MPLS lookup, doing a lookup on the ingress or the inner payload, and then forwarding the traffic towards the customer. So in the case of a layer 3 VPN, we would have the provider router that is sending an MPLS packet to the provider edge. The provider edge looks at the label number of the ingress packet and says this is supposed to be going to customer edge 1, or this is supposed to be going to customer edge 2. And then we're typically going to be forwarding the packet as the native inner payload, like IP version 4 or Ethernet IP version 6, depending on whether we're doing a layer 2 VPN, like for Ethernet, or we're doing a layer 3 VPN, like for IP or IP version 6. Now, the last of these three, the provider device, which again is sometimes referred to as the label switch router, the LSR, is going to be the one that exists only in the service provider core and only has links to either other provider edge routers or to other provider routers. And we'll see the thing that is most important about this is that the P router is only going to be making its decision on MPLS labels. So when we looked at that example, when we were tunneling the traffic over the BGP free core, this is the ultimate reason that the P routers don't need to run BGP, is that they're only making their decision based on the MPLS label. They're not making their decision on any of the upper layer payload information, like the IPv4 packet or the Ethernet header that can be tunneled inside the MPLS packet. Now, in terms of the device operations, as I mentioned this already, the provider edge router, when we receive traffic in from the customer, we're going to be adding a label to the stack, or what's sometimes referred to as the push operation or the imposition. The devices in the middle are going to be making a label swap decision and a swap operation, which means they look at the number as it comes in, they change it to a different number, and then forward it out a different interface. And then finally, the exit device, the provider edge egress edge, is going to be running the label pop operation, which means they're going to be removing the label from the outgoing packet, or what's sometimes called the disposition. Now, regardless again of what is the device role, whether we are the P or the PE, we're going to have to be running some type of label distribution protocol in order to do the association between either the IPv4 address and the label, which again we call the forwarding equivalency class, the FEC, the IPv6 address and a label, or some type of layer 2 payload like an Ethernet destination, like an Ethernet MAC address and the MPLS label. Now, regardless of which of these protocols that we use, again, the inner format in terms of the data plane switching is going to be the same. So this means that in some portions of the network, you could be running label distribution protocol. In some portions, you could be running multi-protocol BGP. In other portions, you could run RSVP for MPLS traffic engineering. And we will be able to transparently switch the labels on a hop-by-hop basis, regardless of what the label distribution protocol is. Now, we'll see, though, there are some caveats in terms of which protocol are you using and when can you, or which protocol are you using to allocate the labels and when can you use those for actual forwarding. And the simple way to think about this is you need to look at how is the route installed in the routing table. So what I mean by this is that if you do a show IP route for the provider edge device and the provider edge device is learned via an IGP route, for example, OSPF or IS to IS, it means that you can use the LDP label. But if the route is learned as BGP, whether this is an eBGP route in terms of inter-ASL3 VPN or inter-ASL2 VPN, or whether this is an interior BGP route, an internal BGP route, this means that we would have to use the BGP bound label for anything that is installed in the routing table as either eBGP or iBGP. Then last but not least, anything that is pointing out an MPLS traffic engineering tunnel. So if we show IP route and it says the destination is via tunnel 0, and tunnel 0 is MPLS traffic engineering, it means that we're going to have to use the label that is bound through RSVP, the Resource Reservation Protocol. And we'll see in terms of inter-AS-L3 VPN or inter-AS-L2 VPN, this is one of the big hurdles to try to get over in understanding how the label stack fits together and how the end-to-end label switch path is formed. We always need to look up on a link-by-link, or not a hop-by-hop basis, I should say, how is the destination being learned, and that is going to determine what particular labeling protocol that we can use. Now we'll see that we will run into problem cases that you might have both an IGP label plus a BGP label and potentially an MPLS TE label at the same time. And if the route is installed in the table as the wrong type of route, you may not be able to use that particular label. Like if I have, again, an LDP learned label, but the route is installed through BGP, it means I cannot do label switching. Or if I have a BGP learned route, but I'm using MPLS traffic engineering in order to get to the destination, then I'm not going to be able to use label switching. And ultimately, we'll see the verification for any of these cases is always going to be the same, is to look at the show MPLS forwarding table, or simply the show MPLS forwarding. So based on the destination that we're trying to reach, which is typically going to be the egress provider edge router, we need to look at how is the loopback address of that PE router installed in the routing table, and that ultimately defines what our MPLS traffic flow is going to be. Okay, so we have a couple questions here. Can we check whether the router is doing downstream on demand or unsolicited downstream label distribution, or is this dependent on the vendor implementation of the code into the device? It usually depends on which protocol that you're using, whether you're using LDP or MPLS traffic engineering versus BGP. I believe there is a way to check what is the mode, and I believe in some versions that you can change it. But normally, you don't even really worry about that. Whether the label is unsolicitedly set outbound or whether it is implicitly or explicitly requested inbound, the end result should be the same, that you have the binding between the label and the IPv4 loopback address, which again is going to be our forwarding equivalency class. But we will touch on that in a little more detail when we look at this on the CLI. From a control plane point of view, there technically is a difference between how the label allocation is actually done. There's a question, how does the VPN label for a particular FEC located in a VPN in BGP get advertised before the MPLS topology is up in the control plane? And this will actually be a very important point that we need to talk about, because there are multiple control planes in MPLS. There's going to be the core MPLS control plane, which is typically formed from LDP, and then there's going to be the VPN control plane that's typically bound through either VPN v4 BGP or VPN v6 BGP, and if one is working and not the other, then ultimately the traffic forwarding is going to fail through the service provider core. So to answer your question in short, yes, there can be a case where BGP is working and LDP is not, and the end result is that traffic is going to get dropped. There's another question, when forwarding regular IPv4 within the global table, i.e. having only one label from one PE to another, is the IPv4 time to live decremented by each label swap operation, as is the MPLS TTL? Typically, it is by default. So your IPv4 time to live or your IPv6 time to live is going to be copied by default into the label, and then when we do the disposition, we take the label, we decapsulate it, and then send the native IP packet. The TTL value is copied back into the IP header, and we'll see one of the end results of that is whether the customer is able to do a trace route through the MPLS core. If the TTL propagation is enabled, which is typically the default behavior, they will be able to see what are the label switch routers or the provider routers in the middle in terms of layer 3 hops in the network. But there is a switch that you can turn on or turn off to say, do I want to allow the time to live to be copied or not? There's a question I read somewhere that for Ethernet interfaces, Cisco will always do unsolicited downstream in LDP, while for ATM interfaces, it will downstream on demand. Yes, because that has to do with a feature called cell mode MPLS. That cell mode MPLS is binding the MPLS label into the virtual path identifier and the virtual channel identifier, which is the VPI VCI. It's basically a legacy technology now, but it did have a different label allocation mechanism. But the end result is the same, that whatever your destination prefix is, it should have a label associated with that. And as long as the LDP adjacency forms properly, as long as the BGP adjacency forms, as long as the MPLS traffic engineering tunnel is up, you should have the label binding. And typically any type of problem you would run into the control plane doesn't relate to whether the label was allocated with unsolicited downstream versus downstream on demand. There's a question, in today's routers, is there a significant difference in performance between label switching and regular destination-based routing? There's typically not a performance difference between them, but there is a difference in terms of what hardware supports what types of features. So in certain core routers, you can buy line cards that are for MPLS label switching only, which means that they don't have to have the ASIC information built in for forwarding IP packets or forwarding IPv6 packets. And ultimately, it's a cost issue of the per port cost of an MPLS only card versus a multi-protocol card, which could be doing like regular layer 3 forwarding, or it could be used as a provider edge termination point that we're doing the label imposition on. So in general, no, there's not really a performance difference, but there is a difference in the hardware of what particular boxes support which features.